Hello everybody, it's Dr. Carroll here. University Chemistry 1111, UChem 42U is the other designation. We are looking at the first lecture in the last chapter of Chem 1111, Chapter 9, all about solutions. Recall that we have looked at gases, liquids, solids. Now we're going to mix them up and talk about the nature of solutions, solubility determinants, characteristics of aqueous solutions, colligative properties, and a little bit more about between solutions and mixtures. So you can read the motivator to begin with. In our mini text, we are on page 412. And what is a solution? A homogeneous mixture of two or more substances. Yes, you can have more than two things in a mixture, in a solution. For example, air is a solution, and there's like 6, 7, 8 different things in air, with nitrogen being the solvent. So if I scoop up some sand and pebbles off the beach, then that's a heterogeneous mixture. It's not a solution, but a solution is a homogeneous mixture because the composition is the same anywhere you look. If I have a can of Sprite, the Sprite solution will have the same concentration of sucrose molecules per liter of water. So let's take a look at some of these cases. Components, the smaller part in a solution is the solute, the larger part is the solvent, and the solvent determines the phase. And we see some examples of if we have a gas solution, so this is the phase here, then you could have gas dissolved in gas, like helium dissolving in oxygen or air. We could have humid air, which would be like water dissolved in the air, like water vapor dissolved in the air, or even, yeah, that's what they have there for liquid. Now we could go on about humidity forever. I'm not going to bother with that. You could have a solution, a gas solution, where you have iodine, a solid, subliming. So above iodine in a beaker, let's say, you can have the iodine in the gas phase along with nitrogen and oxygen. Humid air, again, you could have liquid water, feel it above the nitrogen and oxygen. It's a very humid day today. Who knows what day it's like when you're reading this, but today while doing it, it's very humid. Liquid, we can have carbon dioxide gas dissolved in water. Liquid, we could have vodka, so we could have ethanol, which is grain alcohol, as a solute, and water as a solvent. We could have a salt solution, so, and that's the one we'll look at the most in this chapter. So that is a solid dissolved in water. Ocean water is an aqueous solution. Aqueous means water is the solvent. Some people say aqueous, some people say aqueous, and there's lots of solutes in ocean water, that's for sure. Then we could have solid has our phase of the solution, so solid being the solvent, and you could have hydrogen gas stored in an alloy, and that is a interesting system helping to get hydrogen powered cars. We could have liquid plastics dissolved in solids. So that's a liquid in a solid. We can have solid in a solid, and that's when I think of as like pure alloys, like steel. So you could have manganese, and carbon has our solutes, and iron has our solvents. Okay, and then there's methods for how to make these. Okay, and you can read that on your own. Now you can have different compositions of solutions, so you have to specify the concentrations of the solutes as well as their identities. Lots of ways to express concentrations, each having advantages and limitations. It's always a ratio. The amount of one component, usually the solute, is in the numerator, and some other amount, either the solution or just the solvent, is in the denominator. So there's different systems that are used. This textbook does not talk about all of them. So neither will I. I'll use what the textbook does. If there's some assignment questions that use others, then we'll revisit this. So one common kind is mass percent, which is sometimes called W/W or M/M. And it's the mass of the solute over the total mass of the solution. I need my calculator here, don't I? So for example, dissolving 12.5 grams in 100 grams of water gives a solution that is 11.1 mass percent. So you would have your solid is 12.5, then you'd have, well, the total solution is the solute plus the solvent, so it's 112.5, and you get times 100, 11.1%. Okay, so that's how you get mass percent. Molarity, we've seen that before, is the most common concentration for aqueous solutions. Now, it is temperature dependent, so that's why molality is actually technically a better choice, but molarity is used a lot. Number of moles of solute divided by the volume of the solution. And in this chapter, we're going to use lowercase c. For molarity, I have seen capital M, I've seen it italicized, but we're using parts of this book, italicized M for molar mass. So just get used to the fact that lots of letters are used for lots of things. So concentration is moles of solute over the total volume of solution. And it's convenient because we're often measuring liquids by their volumes. But again, if the temperature is different, then it's not so good because, for example, let's have a volumetric flask, and here's what's called the meniscus. Okay, so the temperature increases, then the meniscus is going to go to a different place, and you might end up diluting things. So this isn't a good drawing at all, is it? Okay. Anyways, you just hopefully one day you'll do labs using volumetric flasks, and you can see that they're temperature dependent. Okay, what does this do? Erase. Oh, look at that. I didn't know that was there. Look how quickly it just erases. Oh, but then it stops. Okay, oh, no, there we go. Well, this is fun. It's trying to remember the last scribble that I did in that great drawing. You're always saying, go, Dr. Carroll, go finish it off. There you go, hooray, okay. So there is a way to measure concentration which isn't using temperature dependencies, and it is molality. Now, sometimes it's written as, I need my picture. My drawing has an italicized M, but this book likes to use B. A UPEG recommendation is either M or B. We use B to avoid confusion with mass. Fine, okay. So we'll use B for molality. There will be times when I'm going to forget and just use little m, or else I'm going to just write the word molality. It's not molarity, it's molality. It's not morality, that's another thing altogether. Molality is the number of moles of solute divided by the mass of solvent, but in kilograms. Okay, so there it is. There's my definition. Molality is moles of solute over kilograms of solvent. Now, those are both masses, so those values don't change with temperature. So that is a useful calculation. There are times when molarity and molality are close to each other, but not always. So let's look at an example here. Hydrogen peroxide contains 3% H2O2 by mass. Assuming the rest of the content is water, what is the molality of this disinfectant? So that is the stuff you get on the at the pharmacy. So you see here 3% H2O2. Now they don't even, I forget what USB stands for, but they don't say that it's mass by mass. That's an assumption. So we want to find things out. So if we have 100 grams of disinfectant, which is always convenient to do, so 3 of those grams are hydrogen peroxide and 97 are water, right? Because then your mass percent is 3 out of 97 plus 3. So 3 out of 100 times 100 gives me 3%. Now what did they want us to get? The molality. So we have the molar mass of H2O2, molar mass, and then we can get the moles of H2O2, which is the grams, 3 grams over 34.02, so 0.0882 moles. And the mass of water is 0.097 kilograms, 97 over 1,000. So molality is moles of solute over kilograms of solvent. There's your units, moles per kilogram. So 0.0882 moles divided by 0.097 kilograms. We could try to get molarity here. That'll be moles of solute per liter of solution. So the moles of solute is 0.0882. The liter of solution, now we don't know what that is. We can make an assumption that 100 grams is, if it's mostly water, it's going to be close to 100 mils or 0.1 liters. So I could divide by 0.1 and go to 0.882 molarity. So I could say molarity, though it wasn't asked for, would be approximately 0.0 or 0.88. Can't do really more than that, moles per liter. Okay, there I'm assuming that the density of water is 1 gram per mil. I could get the mole fraction if I wanted to it wasn't asked for, but I could get the mole fraction of H2O2. Mole fraction of H2O2, we looked at mole fraction in the gas units, is the moles of H2O2, which is 0.082 over 0.0882 plus the moles of water. How much water we got? 0.97 grams, so 97 over 18.02. So let's figure that out. 0.0882 divided by 0.0882 plus 97 out of 18.02, 0.016. So that is the mole fraction of H2O2, if you were asked that. Okay, let's try the next one here. Determine the molality of a sugar solution that contains 3.94 grams of sucrose dissolved in 285 grams of water. So molality, so that is B is going to be moles of sugar, so that's going to be 3.94 out of the molar mass of sugar, which is 342. If you want to look that up, divided by 0.285, right? Not 285, you got to divide by 1,000. So it's 0.285. So 3.94 divided by 342, and then all that divided by 0.285, and I got 0.04 moles per kilogram. Or if I want a bit more sig figs, 0.0404, a bit more digits, whether you want to call them sig figs or not, you can deal with that, moles per kilogram of solvent. Okay, so you should know how to get molarity, how to get molality, how to get weight percent. There's another one called weight per volume, another one called volume per volume, but those ones we won't use as much. Mole fraction, we've already talked about it, and we've already talked about parts per million and parts per billion in chapter 2, so I'm not going to re-discuss that. So let us jump straight to a classic kind of question where you got to look at different kinds of concentrations. Of course, there's all sorts of fancy computer programs now that can do lots of this stuff. So example 9.2. I'm going to do that one. Yeah, let's do it. Okay. Concentrated aqueous ammonia, also known as ammonium hydroxide, is NH3 plus H2O, so it's NH4OH, is 14.8 moles per liter and has a density, so here they're using molarity, that's a symbol capital M for the unit, moles per liter anyways, and a density of close to 1.898 grams per ml. Determine the molality and mole fraction. Okay, we're going to need that molar mass somewhere, I think. We have information about molarity, density, how to get molality and mole fraction. The way to approach convergence from molarity is to choose a convenient volume, something like 100 mil or 1,000 mil, and then take it from there. We know the molarity, so let's look with a liter, which is 1,000 mil. So 1,000 mils contains 14.8 moles of NH3. So the mass of the solution, if it's 1,000 mils of solution, what is the mass of the solution? It's the density times the volume. So 0.898 grams per mil times 1,000 mils. So 898 grams. Okay, and we know that there's 14.8 moles of ammonia in that amount, right? So you multiply by the molar mass of ammonia, 14.8 times 17, you get 252 grams of NH3. I'm not talking about NH4OH, I'm talking about NH3. And then the total mass was 898, so the mass of the solvent, which is water, is 646. So now we got the masses of each, we can get the moles and go to town. Solvent mass to kilograms, so the mass of the solvent is 0.646 kilograms. The moles of the solvent is 35.9 moles. 646 grams divided by 18, or 18.02 grams per mole. And now we can get the molality. The moles of solute, 14.8 moles over 0.646 kilograms. Now you can try something else. You can say, oh, why did you do 1 liter? What if you did 2 liters or 5 liters? You'd get the same answer because it's a ratio. So try it, and you'll see you'll get the same answer. So that's a rather large molality, but it is a pretty concentrated solution, 22.9 moles per kilogram. And the mole fraction of the solute is the moles of the solute, 14.8 moles over the total number of moles, which is the solute plus the solvent, 14.8 plus 35.9. So the mole fraction of the solute is 0.292. Okay? Practice exercise 9.2. Yeah, let's give that one a try here. Determine the molality and mole fraction of concentrated HCl. So that's 36.5 grams per mole, which has 12 molar and has a density of 1.19 grams per mil. So let's assume we have 1,000 mils. So the mass is the density times the volume. Density is mass over volume. The density is 1.19 times 1,000, so 1,190 grams. Okay. 1.19 times 1,000. 1,190 grams. That's the mass of the solution. The mass of the HCl, well, it's the moles. It's 12 moles, right? 12 moles times 36.5 grams per mole. So 12 times 36.5, 438. And then the mass of the water would be 1,190 minus 438, 752. Okay, so now the moles of HCl is the grams, 438 divided by 36.5. Surprise, surprise, it's 12. Of course it's 12, that's what's given to us. And the moles of water is 752 out of 18.02, 41.73. Okay, so then the molality B is the moles of HCl 12 over the kilograms of solvent, 0.752. So 12 divided by 0.752 is 15.95. The book rounds it to 15.9 moles per kilogram. And the mole fraction of HCl is the moles of HCl, so 12 divided by the total number of moles, 53.73. 0.223. Okay, so that's how you do that. Okay, section exercises. Are we going to do any of those? Oh yeah, I guess we're going to do the second one. The first one, brass is made of copper and zinc. This is a solid alloy with brass being the solvent, and copper being the solvent and zinc being the solute. I always get my bronze, my brass, my pewter mixed up. I won't worry about 9.1.3. You can try that as a challenge on your own. 9.1 by 2 parts per million by mass. Nah, I'm not going to bother with parts per million, but I've never seen that one on a test, so I'm not going to bother. But you can try it on your own. 9.1 by 0.2. Okay, so let's go through fairly quickly 9.1.2. Because some of these concepts we've talked a bit when we talked about intermolecular forces. We can have things that are soluble in all proportions, and they're said to be miscible, M-I-S-C-I-B-L-E. Acetone and water can be mixed in any proportion, from pure water to pure acetone. The other extreme is something may be insoluble in another substance. You try to put table salt into gasoline and it doesn't dissolve. And then you can have in between, but there's a limit to how much can be dissolved, and that's what we mean by saturated. So when the solution is saturated, you're in a state of dynamic equilibrium. The rate of dissolving equals the rate of precipitation, and the concentration in that case is called the solubility. It has to be given a specific temperature. For example, 350 grams of sodium chloride will dissolve in 1 liter of water, but at the same condition, only 0.0015 grams of silver chloride will. So silver chloride is sparingly soluble, some would even say insoluble, whereas NaCl is soluble. So the big deal about this is like dissolving like. So polar molecules will dissolve in other polar molecules. In other words, polar solutes will dissolve easily in polar solvents, whereas nonpolar solutes will dissolve easily in nonpolar solvents. But take a nonpolar solute, it's not so easy to dissolve it in a polar solvent. Take a polar solute, it's not so easy to dissolve it in a nonpolar solvent. Okay? And the like dissolves like means that you're going to get the forces of attraction between the solute and the solvent, similar to the solvent-solvent and solute-solute interactions, which enables the possibility for mixing more easily if you have way different kinds of forces. Let's see here, I'm looking at here the methanol, water and methanol mix. The water-water attractive forces and the methanol-methanol attractive forces must be overcome. They're replaced by methanol-water attractive forces. They both have OH groups, that makes them alike. They're ready for hydrogen bonding. The net result is the degree of hydrogen bonding in the solution is about the same as in either the pure liquids, making these two liquids miscible. Okay, so they can easily mix. Octane and cyclohexane are also low polarity, only have dispersion forces holding them together, and they're about the same values, so that makes them miscible. So if the values are around the same, it's miscible. Water and octane aren't though. Octane is a lot weaker than water, and octane doesn't form hydrogen bonds. The only forces between water and octane are dispersion. Hydrogen bonds are way stronger than dispersion, so to break up that hydrogen bonding network in the water, the energy needed to do that is far greater than the stability gained from octane water dispersion forces. So they are nearly insoluble in each other. Okay. Same reason water and cyclohexane are also insoluble, and they form two layers. When you do more organic chemistry, you'll talk about an aqueous layer and an organic layer. And the organic layer usually floats on the aqueous layer. Okay. Now acetone is an interesting thing because it has a polar bond, CO bond, and a 3-carbon bonding framework. Acetone mixes with cyclohexane and with octane, even though those are non-polar, but you have these 3 carbons here. And that allows to be a versatile solvent. It dissolves both polar and non-polar substances, so it can dissolve hydrocarbons. Not super heavy hydrocarbons, but you can even go up to octane. It's interesting. But it's got that polar CO bond, so it also dissolves in methanol and water. So it's versatile, and there are some that are versatile. Look at acetone, it's used to clean and rinse glassware. Of course, There's some safety issues with it. You can read about those. Possible carcinogen. For nail polish remover, which acetone has been used for, I would get the non-acetone ones now. Okay, so give a molecular explanation for the following trends in alcohol solubilities in water. So here we see that propanol, you got lots of hydrogen bonding, so it is miscible in water. But you go to hexanol, we got this long carbon chain, and it will not be miscible because this nonpolar zigzag chain is going to dominate over the hydrogen bonding. Okay. So longer chain alcohols are progressively less stable, less soluble in water because of the hydrocarbon chain gets longer, more destabilization is involved in inserting the alcohol into the water matrix. The Matrix, that's a movie, right? Then do on practice exercise 9.3, dispersion forces increase some liquids in cyclohexane. Okay, water, methanol, ethanol. Okay, so again, you aren't going to have hydrogen bonding here because your solvent is cyclohexane, which is used a lot in organic chem, and ethanol has the highest molar mass of the ones listed, and so it's not a lot. Oh, sorry, it's completely miscible. Wow, okay. Whereas methanol is just 5%. So there's greater dispersion forces, and that's why it happens like that. So that like dissolves like is just a rough tool to help us understand. But to really get into details, you got to do a bit more analysis. Solubilities of solids. Okay, what do we have here? Molecular solids dissolve readily in solvents with similar types of intermolecular forces. So, for example, nonpolar iodine, diatomic iodine, is soluble in nonpolar liquids like carbon tetrachloride. Hydrogen bonding allows water to dissolve materials that form hydrogen bonds, like sugar, glucose. They're highly soluble in water. You get lots of hydrogen bonding. That's key. And so naphthalene only has dispersion forces, so it's nearly insoluble in water. The best solvent for molecular solid is one whose intermolecular forces match the forces holding the molecules in the crystal. So for a solid held together by dispersion forces, good solvents are nonpolar liquids, such as carbon tetrachloride, cyclohexane. For polar solids, a polar solvent such as acetone works well. Okay, here's some vitamins, example 9.4, and we see fat soluble versus water soluble. So which are which? And so the polar ones are going to be water soluble, and the nonpolar ones will be fat soluble. But again, it's hard to tell sometimes because you've got these long chains. You're like, let's look at vitamin E. I'll look at it from here. Okay, so vitamin A, D, and E are all fat soluble. A, D, and E. Okay, so what they're saying is that the nonpolar areas win out over the hydrogen bonding, right? Those are long nonpolar areas, and the hydrogen bonding isn't sufficient for that. Look at this long chain here in retinol. So vitamin E, retinol, vitamin D, those ones are all going to be fat soluble. It's interesting, we got a little bit of biochemistry going on here. The other ones, vitamin B5, vitamin C, vitamin B6, those are water soluble because you see lots of hydrogen bonding. Look at the vitamin C, my goodness, 1, 2, 3, 4 hydrogen bond regions. Vitamin B5, 1, 2, 3 of them. Vitamin D, oh no, yeah, vitamin D, not much, right, good. Vitamin B6, and 2 of them. Oh, then you also got NH2. So that's useful. A little bit of biochem there. Uric acid versus testosterone. So uric acid, you got lots of NH hydrogen bonding regions, so that's going to be water soluble, whereas testosterone will be fat soluble because it's just got only one OH. Okay? Some quick other things here, not the main focus. Metals do not dissolve in water, but they can react. Okay? And they don't dissolve in nonpolar liquid solvents. Okay, then you can talk about forming gases, fine. Alloys, liquids dissolving in another one, amalgams, fine. Now this part here, sort of looked at before, grade 12, different amounts of energies to get the cation and the anion in a ionic compound into solution through hydration spheres. Okay, so I'm not going to worry too much about that. Characteristics of aqueous solutions. I don't think this one we discuss much in the chapter. Yeah, this part we usually leave out. So I'm going to leave it out for now. Yeah, this one we don't get to so much. Same with gas solution equilibria, which is something called Henry's law. That's usually left out. If I have to go back to it, I will. But usually that's not done in the course. There's only so much we can do in the course, right? There's lots of things going on. We can't talk about everything. But if we have to talk about this, I will go back and do that. Colligative properties, that's the next major topic, and we'll do that for lecture 2. Okie dokie.